Hello, everyone. Good afternoon, and thanks for coming to this talk. We have here with us Suri, who is a former Professor Vance's student, PhD student. Now she graduated and she's now working in Germany. And she's going to tell us a few things about the next leap to characterize exoplanets, atmospheres in the ELT era. So please go ahead and the screen is yours.
You can see my screen.
Yes.
Okay now, right? Yeah.
Yes.
Okay. Hi everyone. My name is Suran Kanarakdi and people call me Suri. I am currently at the Max Planck Institute for Extraterrestrial Physics. So when people ask me what I do, I will tell them that I am an instrument builder. So I have been working on different instrumentation for the astronomical observing. So in the left-hand side here you can see the name of different projects that I have been working on, from the infrared to the UV. And then currently I would like to expand my horizon to space mission. So I jumped to X-ray, and these are the projects that I help to characterize and testing for the upcoming X-ray missions like SWARM, Einstein Probe, and Athena. So the driver of my research is that I would like to answer if we are alone in the universe, and by doing so, I have to ask some question like, if there is a planet like Earth out there, and what are they made of? Are they rocky? Are they full of water? Or are they lava world? And can we make a detection to infer habitability? And my goal is to deliver precise and reliable instrument to answer these fundamental questions. And by doing so, I aim to study exoplanet, or the planet outside solar system. It was first discovered in 1995, and until now we have more than 4,500 exoplanets at different types that have been found and confirmed, but only a handful of them still that is ready to be characterized for their atmospheres. For the method that I'm very much interested in to study exoplanet is with spectroscopy, and we can do so by two different methods. So first, we detect and confirm the planet by the method called radial velocity. So when the planet orbits around the star, it creates small shifts when you observe the signature of this planetary system. So this different color of the light, and we can measure the radial velocity, and that will tell us like what is the mass of the planet, how long does it take for the planet to orbit around the star. And later on, after you get some planetary system that you are interested in, you can characterize for their compositions combined with the method called transit. And later, we do the study of the atmosphere through transmission spectroscopy. So with the two methods, I would like to point out two projects in this talk. So first one is STARDIS, which is the project I started when I was a PhD student here. So STARDIS is, it stands for the Tau Ayuk High Resolution Wideband Spectrograph, and was PI by Professor Leonardo Vanzi. And the aim for this project is that we want to study a type of star called M stars. They are very faint star in the sky, but they are abundant. So like 70% of the star in the sky are M stars. And the reason that we don't see them is because their peak energy is in the infrared, is where we don't have the visibility through our own eyes, so we cannot see them by eyes. But what make them very interesting is that they have this green zone, we call it habitable zone, which is the area where it has the right temperature, not too hot and not too cold, but just right for the water to stay liquid. So water is one of the major factors that would indicate you can build some kind of habitable environment for life or not. And with M star, you have this zone very close by to your host star, and that make it very interesting to study. And what I do is first to design, use the optical design to make the spectrograph. So in this spectrograph, we plan to do the fiber feed spectrograph, which with the image slicer, so that we can boost it to high resolution to about 66,000 of the resolution over the small wideband, which is the wavelength range of 0.8 to 1.12 at the time I was working on, but right now there is a slight adjustment to these parameters. And the grading, we use the eggshell grading, which is part of the high resolution radial velocity method. And we cross this first by a VPH. And then we will receive the light from the system with a detector. And our calibration would either be light or it can also be Ethelon calibration system. After the optical design, we do the optomechanical design. So we build the supports for these optical components. So, and then later on, we can build it. So if you have visited IUC, you will see at the corner, there is a lab where I lived in the 2 or 3 years. And so this is the prototype that I was building in that lab. So we have in the front here is the collimator. And what I'm doing in this video is to do the alignment of the instrument. So we try to get the best signal out of the instrument, basically. So right now we try to do the collimation, and then here is the eggshell mounting. So there is the eggshell grating inside this mount. And then I will put later on, this is the fold mirror. And so this prototype is built on the design. So combined with the optical design, optomechanical design, we have the VPH, and then we have different lenses. So this prototype has been done like 3 years ago, but I believe that now we have slight adjustment to the design, and it might not look the same anymore. But yeah, just so you have some idea that we work on in IUC. So what do we do then? If we want to observe the planet that orbiting around the star, they will essentially create the sinusoidal light curve into our spectrum line, right? And with the detector, what we are going to see is something like this. So this is like 1K detector. And if you zoom in this region, you can see the very top panel here. There is the small black line, vertical line that move back and forth. And these are the shifts that I was talking about. So we have the dual fiber source, which is the plan instrument. And then we have the calibration fiber at the same time. That's what's the plan. And after we have the detector image, so assume that we observe an object in the sky, later on, we would have to deal with the data reduction. And to one of the major problem of radial velocity that I'm also looking into is that how do we separate the signal from between the star and the planet like clearly? And one of the methods that we've been using is to use Bayesian inference to model the stellar signal, we call it stellar activity, model as red noise, and that later we can subtract it from the whole signal, and later on we can get the real planet signal. And that's still like ongoing process and like one of the big topic that people in the community are still talking about. And after the radial velocity instrument, I moved on to my first postdoc at the Center for Astrophysics at Harvard and Smithsonian. So as I mentioned, after we have the planet that we think that it might be rocky, it might have some atmosphere, we want to study the atmosphere of the planet. So if you see in this image, we have the star. This is just the Earth and the sun. We have the sun, we have the Earth as an example. And this thin blue line around the Earth is the atmospheres. And imagine that what we are trying to study now is to detect this thin line on the planet outside solar system, right? And the technique, as I mentioned, we use transmission spectroscopy. So when the planet transits the whole star, the atmosphere will glow, and we will be able to detect the color signature or the spectrum that shows the chemical compositions of those planets. And what I'm interested in are the biosignatures. So what are the signatures that would be essential for life? And in the next few years, it will be a very exciting time for the study of exoplanet atmospheres, because we will have 3 giant telescopes on the ground. We have GMT and ELT, which are actually going to be on chilly ground. And then we have TMT, and each of these telescopes will be equipped with high resolution instrument in the visible and in the infrared. And that we will be able to study these atmospheres from the ground. And in space, we have Ariel, which is the dedicated mission that would be launched in 2029 or so. And the aim of Ariel is to have a wide wavelength range study of the exoplanet atmosphere. In particular, the very big planet like Jupiter-like planet. And then due to launch at the end of this year, that we are keeping our finger crossed, is the James Webb Space Telescope, which will also be able to use to study exoplanet atmosphere. And in this plot is the example of the signal to noise of the James Webb Telescope that assume if we have Earth around different type of stars here, we will be able to see different signatures like methane, water, carbon dioxide, carbon monoxide, nitrous oxide, ozone. And there is one missing piece in this image, which is oxygen, because oxygen is actually lies around here, which is in the visible, but James Webb will focus more on the infrared part. But the team also know that the oxygen is important, and so they also try to find a way to get the oxygen from James Webb detection, which is called the O2XCIA, which basically the oxygen and collide with some other molecules like nitrogen, for example. And that's for James Webb Telescope. And what about the ground-based observation? If we focus on the ground-based, this is basically the signature of the Earth atmosphere that we have, or the signature that is essential for life. And the goal for this whole study is to find another Earth that has this similar signatures. And so my study focused on oxygen, and it's slide here, as I highlighted in blue. Why do we need high resolution? So if you imagine on other planets, well, on Earth, we have clouds and hazes. So cloud, we know what cloud is. Cloud is basically the collection of water droplets in the atmospheres. And hazes are more like foggy mixture of aerosols in the atmospheres. And if we want to look through clouds, usually we can't, because it's blocking what we're supposed to see on the other side, right? Like when we do astronomical observation and it's cloudy night, we don't get any information. That's just how it is. And the way that we try to beat that problem on the other side. So if we have cloud on other planets, not just on Earth, there is the study that try to estimate how can we do that. So with the same, here it said transit depth, which is the level of signal basically. So if we have the low resolution is R, and if we have like 100 of the resolution, we basically get the flat line. And if we increase the resolution to 100,000, we essentially get much more information into our spectral feature. That's how we would beat the cloud on the other side of the planet. And one very interesting aspect to have high resolution information is that some of you may know that oxygen on Earth is not there at the beginning. So it just happened somewhere like 2 years ago. So in the beginning, we don't have oxygen, and start with we have cyanobacteria and create oxygen, and then we start to accumulate those oxygen into atmosphere after a while. And with the high resolution data, this resemble the green one, resemble the very early Earth that we have very low level of oxygen, and then modern Earth has much higher oxygen level in red. And then if we focus on oxygen, we also want to know how high resolution do we actually need. So the recent instrumentation in astronomy typically reach 100,000 of the resolution, and that's kind of limit already with the traditional eggshell like spectrograph, right? But if we want to observe these oxygen molecules in the atmospheres of Earth analog, so first we have to find another Earth, and then we try to study oxygen around those planets. We need the resolution of 300 to 500,000 shown in blue and green here. And then if we add to 1 million or so, we wouldn't have add up more into the spectral feature anymore. So yeah, 300 to 500,000 is kind of like optimal resolution that we would need. Now, if we talk about the upcoming telescope with the ELT, very large telescope. In this case, I give an example of GCLEF. GCLEF is also the project that PUC is part of the consortium. It's the Large Earth Finder. It has a wavelength range of 350 to 950 nanometers, so in the visible. It has different modes of operation from the high, medium, and low resolution. And then it can do galaxy study, and it can also do planet study. So a lot of science will go into this spectrograph work. And if we try to study oxygen, I give an example of the observing planet around M4 stars, we would probably need something like 70 hours of observation with the GMT, for example. But so if our current instrument can reach only 100,000 of the resolution, it's not enough to try to detect oxygen around Earth analog, right? So what we do is, Benami 2018, he proposed this very cool idea of the Habitable Zone instrument. So we have the fiber input, the light into the center here, and in the center we have the reflective surfaces that would reflect the light into different arms. I call these tentacles like arms. So each of them are almost identical. They consist of a collimator, an echelon, and the focusing lens, and then we have output fiber that would inject into G-clef, for example. And what is the Habitable interferometer? You can imagine it as an optical cavity. So there are two parallel surfaces, strictly parallel and highly reflective. If we have the light going into one side of this block, it bounces in between the cavity, part of the light transmit and part of the light reflect back into where it comes from. So just like in this image. And then it has a nickname, some people call it echelon. And in this work, we also use dualon, which is the double echelon. And echelon is not too new to the study of atmosphere. So it has been used in the 90s with the ISO observatory that used to study Jupiter atmospheres, Neptune atmosphere, and they detect a bunch of hydrocarbon molecules. And unfortunately, the project was decommissioned just right in between the time that we detected the first exoplanet ever. But we still have the heritage from this mission in my current workplace here. And what is the advantage of observing with Habitable array? So basically we can decrease the number of transit that we need to get the 3 sigma detection. So when we do the detection, we will need to reach some significance of detection, right? And if we want to get 3 sigma detection, we would need this many transits in order to reach the real detection. And as you can see in the red, it's kind of like the detection we need with the typical high resolution spectrograph. And then if we increase the resolution, we get more. We reach to the 3 sigma here faster than this one, right? And this is basically dropped by 25 to 35%, and 25 to 35% if we translate it into the real observing time is basically 3 to 4 years, because we observe during transit, right? And it doesn't happen all the time. And what I actually do, so that was the instrument concept. And what I actually do is I don't know from the beginning that it was going to work or not. So I try with the prototype. We built this small prototype in the lab on the test bed. We have the tunable laser source feed into the system from the top here. It hit the prism. It go to the left of the image to the collimating lens. And here is the echelon. So part of the light transmit here, and then part of the light go back to where it come from, to the second arm, which is almost identical. And at the end, we have focusing lens and the fiber supposed to have a fiber to go into an external spectrograph. And so we can imagine this unit as like a resolution booster. So we have external spectrograph of say 100,000, and we boost it with FIOS to 300 to 500,000. And our external spectrograph or current external spectrograph is based on VIPA, which is also a type of Habitable that we use as the main disperser. I'm not going to go into detail, but this is what we use. It reached actually the resolution of 150,000. And this is the measurement from the sun. So we have a small setup here with the fiber collimator that we attach to the fiber tracker, solar tracker, and take the light into the lab with a fiber. And then what do we learn from the demo? So with the Habitable profile, we should be able to get this spectral line, the hyperfine line. So the blue one is like from the first echelon or the first arm, and then the second line is from the second echelon. And that's the prediction. And the prototype result, we did get the resolution that we wanted even more. So we get about 600,000 of the resolution. And then with the dualon that we thought, oh, it would have a better light profile, and then we will be able to collect the photon into the profile even more. So with the dualon, our result got slightly better. So if we just have only one dualon, it reached much higher resolution, but with the chain dualons, we get almost the same as the echelon, but the line shape was better. And then the last one that we tried to investigate was the fiber size, if it's going to affect the result or not. And then we found that the larger the core size of the fiber, the lower the resolution we get. So the optimal fiber size would be around 50 micron fiber for this work. And how do we use it? So after we have FIOS, after we have the external spectrograph, we basically inject FIOS into external spectrograph. VIPA spectrograph will have this similar profile as the X-shell high resolution spectrograph. So very high profile. We have VIPA dispersion in the vertical direction, and then grating dispersion in the horizontal direction. And if we cross with the FIOS profile, it goes in the tilted line. And this is how the detector image looks like when you observe the sun. And after we extract the feature of the oxygen band that we wanted to observe, and if I zoom in just this small region, this is how it looks like. You see the very thin line of the Habitable profile, and then we get a fatter line of the oxygen profile. And this is how it looks like in the full picture of just one single oxygen band. So from 759.6 now to 771, so about 20 nanometer here with just one Habitable, not 8. And before I end my talk, I would like to emphasize that, okay, I think that detecting oxygen is important. It's going to be very essential to interpret or to put into the context of habitability. But if you see in this image, you can see different scenario of exoplanet that they all have the oxygen molecules, and not all of them are habitable, right? Only on the Earth scenario. So basically we have to pay attention to the environmental context. We should detect other molecules along with oxygen so we can claim the habitability of the planet, or we should not go too fast to claim that, okay, we take life. Not like that. We should study the planetary system as the full context before we do so. And that brings me to the summary. So today I was talking about FIOS, which is the new ultra high resolution Feviparo-based instrument that we try to detect molecular oxygen around Earth-like exoplanet with the resolution of 600,000. And then one of the ideas, so FIOS is not just for only GCLEF or GMT, but if it can be implemented with all the ELT, it would be great. One idea is with the ELT high risk, if we put FIOS in the oxygen and methane channel, we would have a chance to decrease or get rid of the false positive detection and get biotic oxygen. And that I would end my talk here and get some questions. Thank you.
Thank you so much. It's been a great talk. So I will stop recording now.